Okay, so today we're looking at separable differential equations. And in general, just looking at differential equations, this is a hugely common application for calculus, and it's one that you will certainly see again in university, possibly even taking entire courses just in differential equations. Okay, so today what we're going to be looking at is just separable differential equations. So it's one type of differential equation, and really just an introduction to the overall topic. But even with separable differential equations, we can look at population growth. Okay, we can model the growth of bacteria. We can model population of humans. We have Newton's law of cooling. Okay, in physics. And we have in chemistry modeling chemical reaction rates. So we can take a look at these, but first what we're going to start with is just sort of an easy example to the topic. Okay, so here is our example. Some of you will likely recognize this from earlier on in the course. This is actually an example taken from Lab 3, although we didn't call it a differential equation at the time. So for this one, all that we're trying to do is figure out what our function y is as a function of x, given its derivative, which is right here, and we have our point on the curve. Okay, so first off, just looking at this, if I tell you that the derivative of your function is 2x minus 1, at this point in the course, we're very used to looking at this and just saying, okay, well, if that is my derivative, then y will be the antiderivative of this function. So I would just say, okay, y is going to be equal to, and I would increase my exponent by 1, divide by 2, which would cancel out this 2 right here, and then we would just say, okay, y is equal to x squared minus x. Now, you have to remember here a couple things. You would put in a plus c as the general antiderivative, and this would be fine. However, I want to just explain this process a little bit more because we need a few details when these differential equations start to get a little bit more complicated. So this is very much where we're going with the question. However, let's take a closer look at this left-hand side. We have dy dx, we have the derivative of y. However, we recognize that dy is actually our differential for x, or sorry, differential for y, and dx is the differential for x. So being these differentials, we can actually move these around. We can multiply by them, we can divide by them. Specifically, what I want to do is actually multiply both sides by dx. I'm going to bring the dx over to the right-hand side. And what we end up with then is that dy is going to be equal to 2x minus 1 dx. And now that I have completely separated, on the left I have just my y values, my differential for y, and on the right I have my function of x, and I have here my differential for x. Now I am able to actually integrate. So I can go back. Now I'm going to integrate both sides. So on the left hand side, if I integrate here with respect to y, I'm really just integrating the constant 1. I end up getting y itself. And on the right-hand side, I'm going to do the antiderivative of 2x minus 1. This we just saw before. It's going to be x squared minus x. And then here, I'm doing the antiderivative, so I'm going to put in my plus c. Now fine, this is clearly where we were before. But in the process of doing it like this, some of you may ask yourself a question. Why do I only put the plus c on the right-hand side and not over here with the y as well on the left-hand side? So first off, you could do this. Okay, you could put in two different constants, one for the left-hand side and one for the right-hand side. And you could call this one on the left maybe y plus c1, and the one on the right would be c2, and so on. But really, this is just redundant, okay? Because if I put a constant on the left-hand side, then I could just as easily say that this represents any constant, bring it over to the right-hand side, and combine those two constants together. So there's really no need to put that constant on the left. It is sufficient to just put the one constant on the right. And here, normally I'm going to put it on the right because in general we would be interested in solving for y as a function of x and not x as a function of y. Here we have what we've called before a general solution. and this is a general solution to the differential equation. And I'm just going to call our differential equation now dE. Okay, so fine. We have here our curve y equal to x squared minus x plus c. And that c just represents any constant. So over here on the left we have a slider, and we recognize that really all that c does is take the curve and shift it either up or down, corresponding to whether that constant would be positive or negative. So really, when we're looking at the general solution to a differential equation, what we have is a collection of an infinite amount of curves, sort of one curve here for every value of c that we're looking at. Now, in our question, we were not asked to find the general solution. We were not asked to find this infinite family of solutions. Instead, what we wanted to find was specifically the function y. So how do we then look at all of these curves and figure out which of the curves corresponds to our function? Well, that's where that point comes in. So looking back at the question, we have here this point 1, 0. Now specifically what that means is that if x is 0, if x is 1, y is going to be 0. So going back to our curve, if I put here that point 1, 0, that means that our curve has to pass through that point. And most of these curves will not. In fact, all of these curves will not, except for one. Okay, there's going to be one specific point, or one specific curve that does pass through this point, and that's the one that we're looking for. And for us, you can see that's the perfect curve, and on the left, that corresponds to c being equal to 0. So for this example, c should be 0. Now, visually, that's what it looks like. Let's go back and actually take a look at algebraically how this would work out. So here we have our general solution, we have our point 1, 0, and what we want to do now is find c. So there's always going to be this sort of second part to these questions if you are given this condition that your curve has to pass through a given point. So find c given the point 1, 0, and really all we have to do now is plug in x equal to 0 and y, not x equal to 0, keep saying that, x should be 1, y should be 0. Okay, so if we have y is 0, that's equal to 1 squared minus 1 plus c, and right away we get c is going to be equal to 0, and therefore our specific curve, the only curve that actually passes through that one point, is equal to y is equal to x squared minus x, and this is no longer the general solution. This is what we would call a particular solution. Okay? And this is the particular solution to the differential equation. That satisfies that condition that our curve needs to pass through this point 1, 0. Okay, so this is the particular solution to the differential equation that satisfies what's called the initial condition And our initial condition for this one was that if x is 1, y should be 0. Okay, so this right here, that is our particular solution. And that's something that we will be looking at quite a bit in the future. We have particular solution, and here we have our general solutions. Okay, so this is sort of our brief introduction to how we solve them. Okay, we're going to look at definitely some more interesting ones, but The idea to start off with is that really this is nothing new. Okay, we know how to find antiderivatives. This process right here of separating the differentials, that's going to be maybe a little bit new, but it's not anything that is particularly complicated. So now that we know how to set these up, let's do a couple definitions and then do some more complicated examples.